I hope everyone uh, have, has been doing okay. What should I say before we start? So this is lecture three, right? Because last time we didn't have a meeting. Still, we have obviously 10 meetings for the semester. I think today we can finally, mm, we have had enough of a preamble so that I can at least state some version of this Poincare conjecture, so that at least today you sort of know what the problem was supposed to be. Uh, and again, this was like a problem that Poincare has stated like what, like at the beginning of the 20th century, more or less, I think. And it took like almost exactly 100 years to be completely solved, depending on how you count. But it was over a century that it took to get solved. Many people had tried it and failed. Um, so it was like one of the big problems, which is why you could have obtained $1 million if you had solved it a couple years before. Although probably uh, you shouldn't feel bad because you were probably like 10 or 8 years old when it was solved. So uh, you cannot expect like an 8-year old to solve it when many famous people failed for almost a century. So there's still six more problems if you want to solve them. $6 million if you want some of that money. So let me tell you a little bit more about the Poincare conjecture then. Let's see. Are there any questions before we begin? Well, before maybe I start telling you about this more specifically.
Are any of those other six problems ones that you're trying to solve?
Sorry, what about the six problems?
Are you trying to solve any of the other six?
Well, I think my not really. My research is most closely related to the Jan-Mills problem, uh, which is like the Jan-Mills problem is about the one like about like proving that like some of the quantum, physicists for like physicists have like a thing called the standard model of particle physics. That's like the thing that people at CERN and those super colliders work with, right?
Huh.
The thing that describes like the constituents of protons and neutrons, which are called like quarks, gluons, and other things.
Hmm.
And so the theories that they use for describing that are called quantum field theories. Um, like the things like these quantum field theories, like from a mathematical point of view, they're like, I mean, they're very successful physically. Like in a sense, like that's like the most successful theory that humans have created. Like some of the measurements of particle physics have like, I mean, they're accurate like between the experiment and the theoretical predictions and the experimental like measurements are accurate to parts in a million. Like they're like very like some of the most accurate measurements, and so they're like very successful physically. It's just that in a sense, like mathematically, it's still not clear some of the foundations that are being used to set up the theory. And so like one of the millennium problems is that to show that certain assumptions uh, are actually sound mathematically speaking. But yeah, those can be a little bit of a black hole. You should if you can solve them, yes, but if one may choose just to try more friendly problems at first. Or you don't tell anyone so that you don't sound crazy. So, but yeah, that's like the one that I would understand the most of the remaining six, I think. Um, so just to today, right? As I was saying, I'll try to explain to you what the statement of the Poincare conjecture is. And so just to put it like into perspective, like if you, I don't know if you have been reading the book, but like already if you read chapter 3 as I recommended for today, there's some fancy words that the book starts using. I'm going to, I think for the most part, avoid that terminology as much as possible. But there's a word that the book starts using, which is called manifold. Uh, so if you see this word in other courses in your life or in other books in the future, like for think of this as for us, it's like a fancy term for like universe.
Manifold.
Yeah, like that's like the right way to think about it. Like manifold is like some sort of space, basically. It's like um like I'll tell maybe a little bit more about what they mean by this. But like whenever, like what I'm trying to say is like if I said like one dimensional manifold, like a 1D manifold, right? What you should have in mind for the context of this seminar is that like I'm just saying, oh, what are the one-dimensional universes? So you should take this as being the same as saying what are the one-dimensional universes. And like as we had discussed, like there are like one-dimensional universes like line segments, right? Or a circle. So you could have like a finite interval. You could have like a circle. You could also have like a infinite interval. Like let me put like dot 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 dot, right? Like just to say this is like the actual the full number line, right? Like an
Mhm.
infinite interval. Uh, like for a mathematician, like you would say, oh, this is a one-dimensional manifold. This is another one-dimensional manifold. This is another one-dimensional manifold. What I'm trying to say is that we can just call this like, oh, this is like a one-dimensional universe. This is a one-dimensional universe. This is like a one-dimensional universe. I think for our context, that maybe is less like colloquially, it makes more sense just to use the word universe uh, from that point of view. Um, what makes this like there's like a reason why, more like a technical reason why these things are called manifolds essentially is like the idea is like, you know, for example, when, if I may, if once you start zooming close enough for a circle, right? When you start zooming and zooming in, oh my god, the iPad doesn't allow me to zoom in more. But you know, what happens is that really like the circle, like the tiny pieces of the circle, look more and more like segments, right? So as you zoom in, the circle looks more like a line segment, right?
Mhm.
And so, and for example, like just to make this is why again it's reasonable to be a flat earther, like from many points of view, because like maybe I don't know if these days, but like it makes sense for a long time. So if you thought about what a two-dimensional manifold is, which again I'm using as this being the same as a two-dimensional universe, like the easiest two-dimensional manifold or universe you could think about would be like the XY plane, or just a plane, right? It doesn't have to be like the XY plane. And like maybe if you want, like you don't need to even draw the X and Y axis, right? I'm just saying like a plane. But you could also have like our friend the sphere, right? Or you could even have like a cute thing like the torus, or which again is like a fancy way just to say a donut. Or you can even have like other things, which is a donut with two holes, right? Or you could also have something with three holes. This could also you could regard as a pretzel, right? I think pretzels had usually like three holes, right? Am I correct? So
Yeah.
yes, good. Many things you could eat in the shape of surfaces. But if you think about it, like again, you could always, like the point is like if you thought like that your planet looked like either like a sphere, right? Uh, this is like called like sometimes I get Taurus. Um, like if you lived on any of these planets, right? If these were like the surface of your planet, you actually would probably think at first that you're living on a plane, because again, if you start zooming in, if once you start like really zooming in a lot, you like you'll see that this is not that different from a tiny piece of paper. uh, And something similar happens here. Like you would see that every point does not look that different from a piece of paper. And so as you zoom in, the surface, any of these surfaces look more like a plane or a piece of paper. Is that making sense so far, so good?
Yeah.
So like what I'm saying is like for a one-dimensional universe, it looked like a piece of line if you look, if you zoom in sufficiently close. For these surfaces, it would look like a piece of paper if you look sufficiently close. And like for the three-dimensional case, which is like the ultimately what the Poincare conjecture is about, if you've talked about a three-dimensional manifold, which again is like a 3D universe. And again, we maybe will spend more time talking about certain examples later. But like the idea is like, again, you have like the simplest case. The simplest case for a in the one-dimensional case was an interval. The simplest case in the two-dimensional case is a plane. The simplest case in the three-dimensional case is like XYZ space or like a box, right? So you would have like, this is like the simplest model or the simplest example. Um, all the space, all of the space, or like think of it as a box maybe.
Mhm.
Uh, so these are like the simplest ones. And like the idea of like whatever these three-dimensional universes are, the thing, think of us as being in one of these universes, right? Because our universe in space directions is three-dimensional. Well, right, if you actually think about it, like you actually feel like you're, if you zoom in into your universe, like what do you get? Well, you get probably the room where you are right now watching this video, right? And the room looks like a box essentially. So whatever these three like 3D shapes are, whatever they are, and again I'll remind you some examples soon. Like the idea is that as you zoom in, a creature on this, in these universes, could not distinguish it so clearly from a box. So if you look zoom close enough, it looks like a box essentially. As you zoom in, a creature in these universes uh, would think would find it hard, would think it looks like a box, or this uh, or the XYZ space. So like the key property of like when a mathematician talks about manifold, what they really mean is like this like source of universes with this feature that as you zoom in, um, you do get something that looks like either a segment or a plane or a box. And you can like if you zoom in sufficiently if you zoom in close enough. And so you could imagine like the that you could keep going like a four-dimensional universe. Then if you zoom in, you get like a four-dimensional box and things like that. That's a little bit harder to visualize, but I'm just saying that all these like universes have like the property that is sort of uh, they're like sort of flat earther friendly, because it's sort of reasonable to assume that like your universe had no, was sort of like simple in the sense of like being a line or a plane or a box. It's just you have to go you sort of have to investigate like different parts of the universe to really realize that it may have like curious properties. Like I don't know if you remember the game that we played last like 2 weeks ago, where like you were like with the tubes, where like maybe you went to the roof and then you came from the floor. Everyone remembers that? So if you had, or maybe you went to this wall and then you appear from the other side. So those features like your universe could have, but in order to realize that those features are there, you sort of have to be like an explorer, so that you can like see how the different pieces of the universe, the different regions in your universe are connected to one another. Is that making sense?
Yes, it does.
Yeah, good. And so I'm just saying that the point of like this concept of manifolds, which again we won't use too much, you can just think of universe, is that if you just looked, if you were not adventurous, like, and you just were happy in your safe space, you never left it, then like you would just think you live in a very dull universe. You would like you lived in a line, or you lived in a plane, or you live in this box, depending on which dimension you are. It's only once you go out there and look at different pieces that you realize, oh my god, there are like actually fun things happening. Like with like similar to this Mobius strip thing that we did last time with the belt that I twisted. Like this thing that like you can change from right-handed to left-handed. I don't know if you watch the YouTube video. There's one that I posted that explains it very nicely. But this feature that you could change your handedness, you can only realize it after you have done like a full trip along the belt or the universe. You really would not tell that if you had been just stuck in your like vicinity, in your neighborhood. So you have to go. The moral of this story is, once the lockdowns are over, just go there, out there, and explore things out, right? I just see what the universe is like. Okay, so again, like the Poincare conjecture is something about like about the 3D universes. Just to tell you before telling it precisely what this says, the Poincare conjecture singles out one of these all among all the possible 3D universes. The Poincare conjecture tells you that one has a specific property that none of the others has. So this is like what the Poincare conjecture says. So like again, a first approach to the statement, I'll write like the more precise version soon, is that among all the 3D universes, there's only one of these that has a specific property. Okay, and so I'm going to tell you which is this supposed, which one is like one that's, which universe is supposed to have this property and what this property is. Like, so that's what I'm going to explain today. Um, so far so good. Are there any questions about this up to this point?
No, not from my end.
Okay. Anyone else? Everything going well? So just to like, I may maybe say the obvious because I sort of said it before, but think of them as like for any of these examples, right? Like the universes, like in general, could be finite or infinite. Like this is like the first distinction. Uh, right, like what are cases like of finite universes? Again, like when I say finite, mathematicians really like to call this compact. Fancy name again, but which you may see in the book, but I won't use this terminology. What would be like finite universes that we have talked about? Ooh, something happened.
Yeah, sorry, that was me. Would that be like the space between 1 and 0? It's finite, but it still has like an infinite amount of things between them.
Well, that's a good question. There are like an infinitely many points between 0 and 1, right? But it has finite length, right? So what I mean by finite, I mean, it's true that it has like infinitely many points, right? But it does have a finite size. It has like a finite length. So like this is like a finite interval is finite in size. Uh, is that making sense? A circle is finite in size. A sphere is finite in size. I mean, if you want, for these purposes, like if you didn't want to, I mean, it's not quite, I mean, by here, like finite, I just mean that think of it as like having finite length or finite area or finite volume. If you think about it in that perspective, um, you won't run into any issues for what I'm going to say next. It's a little bit more technical than that, but like just think of it as another way to say it is like you know, like a circle. You can sort of cover it with. Imagine like you take a bunch of like mini intervals. You know, a circle. Imagine that you take mini intervals of like size 1, right? A circle has like length 2 pi, right? So you know that 2 pi, what is 2 pi, like 6.28, right, or something like that.
Yeah,
So
something like that.
yeah, right, so a circle, that means that if I gave you a bunch of like segments, right, like rubber segments, a circle of each rubber segment of size 1, that means that a circle can be covered. You only need like, you even need less than 7 of these segments to cover the entire circle, right? So that any point on the circle belongs to one of these segments. So like imagine like just drawing the segments here, putting them up top of the circle. Like imagine everything is made of like rubber or clay, so that you can just bend things and put them on top uh, of your figure. So I'm just saying that here you need like a finite number, you need like a finite number of segments to cover the circle, right? And like similarly for the sphere, right? For the surface of the sphere, imagine I gave you like planes, tiny planes, like tiny squares made of like again clay or some fun material that you can sort of like deform. And so just that you can paste on the surface, you can glue, you put some glue and you put it on top of the like patches, right? Uh, so like the sphere, like you can imagine covering the sphere with finite patches of planes, right? So imagine like just putting like here. So like again, you can imagine like covering the sphere with a finite number of of squares or patches. Or on the other hand, I mean, almost by definition, right? If you took something like the XY plane or the number line, right? Or the XY plane, right? Those cannot be covered, right? The number line cannot be covered with finally many segments almost by default, right? And the XY plane cannot be covered with finally many squares, right? Almost again by default. Uh, there are more fun things that you could do. Like for example, like you could imagine like taking like a sphere, right? You have your good friend, the sphere. You drill a hole on the sphere, right? Imagine like it's like an orange. You drill like remove part of the skin of the orange, right? You made a hole, and you attach like this infinite cylinder, like you just glue an infinite cylinder to the sphere. Is it making sense? Like the picture. So it's like like it would be like these things the clowns use, right? Like when they have all these weird like balloons that they make like in sausage shape and things like that. So you just put like you did a hole to the sphere, and like you have this cylindrical balloon, and it's just like your balloon is infinite. So so you put like here like a sphere together, a sphere with one hole plus like half infinite cylinder, right? And you should think of this as a universe, right? This would be like a two-dimensional universe, which is sort of like infinite in size. Is that making sense? So I'm saying like things that are infinite can be sort of more look more interesting than just uh, like thinking of them as just being flat things like the number line or the XY plane. Is it making sense so far so good? So like there are like universes. Yeah. I mean, you could do like Medusa type things, right? Like you could have like your pretzel. You have your pretzel, and then like on the pretzel, you also drill holes, and then you put a bunch of like tentacles, infinite tentacles, like coming out of it. So imagine like just drilling holes. So this is like a pretzel with tentacles. So like there are like weird universes that you could just imagine playing around with. Uh, so those like so right like there just happens to be some universes which are finite, others which are infinite in nature. So this is like the first like a useful distinction between universes. By the way, it's like an I mean it's like an experimental question whether like our universe is finite or infinite in nature in from that point of view. uh, like before general relativity, I suppose people always assume immediately that it was infinite just because people before general relativity assumed that like the shape of the space was more like this thing like XYZ. It was just like this uh, infinite box without the I mean, just keeps growing in every direction. Like there are no really phases. Like it's just like infinite in size. But after like the theory of general relativity, people realize that you could actually, in principle, believe that your universe can have like more interesting shapes. That depends on like the distribution of matter in the universe and other things. Has to do with dark energy and cosmological constants. Maybe I'll mention one of those things like near the end of the course. Um, but I'm just saying like it's not like it's like an empirical question what sort of whether the universe is supposed to be finite or infinite in extension. Uh, okay, so we already said about this a little bit. There's also another interesting taxonomy that you could make about universes, which is separate from this problem. Is separate from this, which is that the universes can have boundary or have no boundary. So universes can also have, they can have boundary or an edge or an end of the world. That's how I like to think about that. Or they cannot, they maybe they don't have boundary. These are called closed universes. So let's again think about, let's think a little bit about some examples, like as to how this might look like. So what would be like a universe with boundary? Well, again, the flat Earth is a universe with boundary. Think maybe of this as the continent, and then there is a massive ocean, right? What's the fear if you're a flat earther? Well, the fear if you're a flat earther is that you just reach one of these edges, right? And then what happens? Who knows? So here, the rectangle has four edges, or has right, and after that, like it sort of ends, right? If you just like if you keep walking after that edge, you sort of exited the rectangle, right? Is that making sense? On the other hand, our planet has no boundary. So let's say, what would be something without no with no boundary? Earth has no boundary. If you live on the surface of the Earth, you don't have to have any fears. You can just keep walking around. Like you may eventually keep coming back to the place, to the same places, right? If you walk for a sufficiently large amount of time. But there's no place on the surface of the Earth where you hit like this wall or this edge, and you cannot move past that edge, right? Is that making sense? If you're always on the surface of the Earth, you can just like, again, like the worst is that maybe you just keep repeating, like you just repeat your, or your previous trajectories. But it's not that you just, it's not that you walk somewhere and you face like the end of the surface. Like you never meet the end of the surface of the Earth, which is happening here in the flat Earth model. Is that making sense?
Yeah.
So the Earth has no uh, uh, boundaries. In fact, our friend the donut, this is for dogs. This is why it has that funny sound. Uh, our friend the donut also has no boundary. If you live on the donut, right? If you live on the donut, you just keep walking. Like you can even go do something here for the along the hole. You just walk here all the time, but you never reach a point where you hit like a wall again. Uh, so this has no boundary. Our friend with two hole, this thing has also no boundary. But like, for example, what's like an easy way to create a boundary? Here's again something with boundary. Well, take our friend the donut, and you were hungry, and so you eat part of it. So this is like a partially eaten donut. Is that making sense?
I'd say so. Yeah, we're just it creates like a sort of like stoppage to that smoothness and that roundness of ability to travel across and all that.
Right. So imagine that I literally, right. The thing is like the point is that here you're moving without problems, but what like once you get to this point, right? Like the difference, like what's happening here, like just to explain it a little bit better, like the thing is like if you're in any of these points on the donut, like the ones who were not victims of your mouth, you can always move like north, south, east, west, right? Or at least that's how it seems from the perspective of someone on the donut. Uh, when you reach to this edge, now this edge looks like a circle, right? If you think about it. So this is like the edge or boundary, which is like a circle. And when you're on the circle, now like again, you can sort of still move along the circle, but you like here you can sort of move in two different ways: north, south, east, west. On the circle, you can only move like depending on how you want to call this, like east, south, or sorry, east, west, or north, south. So I'm just saying like the freedoms that you have when you reach the edge have your motion has been limited somewhat once you reach the edge. So here you can move in fewer ways. That's what I'm trying to say. On this on this edge, is that making sense? So for example, I think it's maybe easier to look at it from the perspective of the flat earther. Yeah, like there are things like you can no longer do freely. For example, like again, if you look at the boat from this perspective, right before reaching the edge, the boats can still do like north, south, east, west without problems, right? But once you reach the edge, the boat better be careful, because like maybe the boat can still do some like this motion without issues, right? You won't exit the world from that moving along that direction. But if you try to move in this way, this is like now problematic, right? This one is problematic because it might like force you out of the world. So I'm just saying that once you, like the point of the edge is that like then once you reach an edge, there are sort of directions that become forbidden, because if you take those directions, then you're kicked out of the universe. Is that making sense? Like the universe being here, the flat earth, or the universe being the donut. So like the point is that on the on the circle, once you reach this circle, the end of this partially eaten donut, now you cannot move as freely as you could have done before, because before you could always like do this north, south, east, west thing. And so there are things with boundaries. There are things without boundaries. Usually people assume that the universe has no boundary. So maybe I should mention this. So we won't worry too much about this thing. Is that okay?
Yeah.
Good. And now we're almost there. We're almost there to the Poincare conjecture. There's only one more thing that I have to tell you, which is simply connected. So here's the issue. Here's the problem. If you want to know, this already, again, if you have read the book, this is partial. It starts being mentioned in the book, maybe in chapter 3 or chapter 4. I don't remember right now. Why don't I have a sphere here? Do I have a sphere? I should have a sphere. Interesting. Oh yeah, I have a sphere. Wow. This is a sphere. I mean, ignore the legs. Right? This is a sphere. This is a donut. Right? So here's a question. How how could you tell that you live in a sphere? How could you tell that you live in a donut, right? On these torus, how can you tell that without taking a spaceship and like just seeing it from the outside, right? That will be considered cheating in this course. You cannot take spaceships because if you think that the sphere is your entire universe, then where is the spaceship going to take you, right? If you think that the donut is the entire universe, the surface of the donut, where would the spaceship take you? By definition, you cannot exit the surface, right? So you cannot look at the universe from like you standing here on your spaceship looking at the donut. That's cheating because that's like you need to exit the universe, the planet to look at it, and that's not something we could do. For example, if you wanted to find out the shape of our universe, because you're gonna, by definition, you cannot look at the universe from the outside, right? Is the issue more or less clear? So like the question is how to distinguish the two, right? Is that making sense, that the problem that we have?
Yeah.
And here's the answer. The answer, I mean, this is not an answer because like this is almost like, I mean, until I tell you what the property is, what the property means. But the answer is that the sphere is simply connected while the torus or the donut is not. So here's the answer. The sphere is simply connected while the torus or donut is not simply connected. Okay, what do I mean by this phrase, simply connected? So let me tell you what that means. What is simply connected? So imagine that, again, like the more precise, like I'm giving you like a heuristic picture of what this will mean. But what simply connected means is that you live on the surface of the sphere, and you are on the sphere, you can draw loops, right? Imagine drawing a loop on the sphere. Let me draw, like, you take a point and you draw some loop on the sphere. So draw a loop on the sphere. Okay, everyone visualizes it, right? A closed loop, that's what I mean. I don't know, maybe that's redundant, but like just to emphasize it.
Mm.
This is something you can do in your universe, right? You just buy some paint and literally you start dropping paint on the universe, right? Like imagine taking some, like you have some paint, you walk on, you do your trip, you start like tracing out some curve, some loop on the, and then you just have to return where you started. So imagine maybe this is where I started with the dropping paint, and I just take some funny, some path, and I get back to the same place, and that's my loop. So this is something that can be done, right? You can draw a loop on the surface of the planet without having to take a spaceship, without having to exit it, right?
Mm.
But if what happens in this case is that you can imagine that in the case of the sphere, you can sort of imagine that you can shrink this loop with while remaining in on the sphere, right? Like so you can imagine that you start shrinking the loop. So this is like a shrunken version of the loop. Right? And it keeps getting smaller and smaller, right? So what I'm trying to say is that on the sphere, this loop can be shrunk. Shrunken, is that a word? Or is it Shunked. It's a weird word.
I
As
think
much,
shrunken is a word.
yes, I think so, right? As much as you want. And all these small new versions and all these new loops are still on the sphere, right? And all these new loops is that making sense? So again, imagine that uh, on this loop, like you could easily have bought different colors and have done like a walk along these loops on the sphere, and you get these paths, right? So like the point, like the property of the key property of the sphere is that like the loops can always keep being shrunken as much as you want while remaining on the surface of the sphere. That's what simply, I'll say it more precisely, but that's like the key of simply connectivity. But what happens in the case of the torus? What about the case of the torus? Again, we have our planet. And this is the torus, right? And the point is that on the torus, like what I'm claiming is that there are loops, right? Where no problem, right? There are loops that you can shrink without any issues, right? This loop, you can shrink without problems, right? Without, and by that I just mean that you can shrink it by drawing smaller loops on the donut, right? On the torus. But what about this one? Everyone sees this? Like I'm drawing like a loop.
Yeah.
What happens if, like, how can you shrink that? Like, you know, to go to shrink this, right? What would you need to do to shrink this? Like you sort of have to go on the to the interior of the donut, right? Do you see it? But I mean, by definition, like I told you, like we're in, like what when I'm talking of the donut, I'm just talking like about the it's like our donuts are not filled with anything, right? Like it's just the surface that we're really interested in. So in order to shrink this loop, right? Shrink this loop. You have to go to the interior of the donut, but that's not allowed because that's not part of the surface, right? You to the interior of the donut, which is not allowed. Is that making sense? The difference between this one and this one, is it clear?
Yes.
And the point is that this is a feature that this is a feature that you will not find on the sphere. On the sphere, all these loops that you could draw can always be shrunken, but on the donut, there are some that can be shrunken, but others cannot be shrunken without exiting the donut. And this is actually the mathematical way of detecting or of saying that there's like a hole, that the donut has like a hole while the sphere does not. So this is like the mathematical way of like detecting holes or saying that the donut has a hole. But like notice that my explanation never talked about holes. It just talked about things that you were drawing on the surface, on the planet. So this is an explanation, like, you know, a hole sort of has to be seen from the outside, but by saying it in this way, I'm explaining things in such a way, I would just tell someone in this planet, okay, draw this loop, try to shrink it, and they would not be able to do it. And then they wouldn't, like, you know, they would know that they're in some different surface that's not the sphere. Uh, but this way can be done but in this, from this perspective, this method does not require you to exit the planet in order to detect like an external observer. So the point is that a simply connected universe is one where every loop that you draw can always be shrunken as much as you want within that universe. So this is like the definition of a simply connected universe. I mean, again, it would really be called a simply connected manifold, but or space is one where any loop that you draw can be made as small as you want within the same universe. Is that okay? Is that like the definition making sense?
Yeah.
And then the claim, if you want, this is not the statement of the Poincare conjecture, but you can think of it as a baby Poincare conjecture. So the baby Poincare conjecture says that among all two-dimensional universes, which are finite in size and have no boundary, among all 2D universes, which are finite and have no boundary. And again, we already explained sort of what it meant to be finite and what it meant to have no boundary. The sphere is the only universe that's simply connected. The sphere is the only such universe which is simply connected. So like what the Poincare conjecture, like again, this is not the true Poincare conjecture, but this would have been from this perspective, the version, like an easier version of it. It's just saying, look at a catalog of all two-dimensional universes, which are finite in size and have no edges, no ends of the world. Among all of them, the only one with this funny property that all the loops can be shrunk to a point is the sphere. There's nothing beyond that. Like this characterizes the sphere among all the other universes. This distinguishes the sphere from the donut, from the pretzel, from all the others. All the other things that you could imagine will have loops that you cannot shrink to as much as you want without exiting that planet or that universe. Is that statement clear? So it's like a classific. It's like telling you, oh my god, the sphere has this particular property that not like it's not shared by any of the other possible universes. And like the actual Poincare conjecture, maybe just to compare it, it's almost the same statement. So it says that among all three-dimensional universes, which are finite in size and have no boundary, now the three-dimensional sphere, I will remind you what that is. 3D sphere, again, it's like the adult version of the sphere that you know, like is the generalization of the sphere. The 3D sphere is the only universe which is simply connected. So again, like the three-dimensional Poincare conjecture is saying, great question. No, there's actually versions in all dimensions. Uh, the answer is sort of known in the others, or was known before. I mean, depending on how you say it, you can like, yeah, for like 2 dimensions you can make the conjecture, for 3 dimensions you can make the conjecture, for 4 dimensions you can make the conjecture, for 5 dimensions you can make the conjecture, and things like that. And like, in a sense, like the answer is known in the other cases as well. I mean, like whether it's true or false. I'm not saying it is true in all the other cases. Depending on how you define things, it actually is false. And so, but yeah, it's a great point. It's like it is it's something you can ask for every dimension. Correct? Yes. Good. But already 3 dimensions is difficult, right? To visualize. So let's not talk about the others. But yeah, you can actually ask it for the higher, the even more complicated cases. Is that okay? So like the way you should think about this is like the Poincare conjecture is like saying of all the list of universes that you could imagine, which are at least finite, have no edges, ends of the world, only one will have this property, and that one is the sphere. And so I should tell you again, maybe remind you in the last few minutes of today, what was this 3-dimensional sphere, if that's okay with you. So what was the 3D sphere? And again, like here's the best way to think about this. Think of a circle, right? A circle is x squared plus y squared equals 1, right? And it looked like this. Hopefully by now I have already convinced you that the circle is one-dimensional, right? Circle was one-dimensional. One way to think of the circle, right? Think of the circle as, if you don't like to write it on the xy plane, think of the circle as being the same as two, like, you know, like a northern and southern hemisphere, where you glued together these two. Think of the circle as two intervals, and you glued the endpoints of the intervals, right? With their endpoints glued. Is that making sense? Like this picture, like you have two intervals, right? And then imagine like you just put some glue at the end of each interval, and then boom, you just paste them together. Is that okay? And so again, this, like the circle had no boundary, but it can be obtained from two universes with boundaries if you sort of glue the boundaries, right? Each individually, each piece has boundary, but it goes away after you glue them. But it goes away after you glue them. Okay, now what's the sphere, like the 2D sphere? This could be confusing, but so just to make it clear, like sometimes a circle, you would call that a 1D sphere. So a circle sometimes is called 1D sphere. So what's the sphere in terms of equations? Is x squared plus y squared plus z squared equals 1, right? In terms of picture, it is our friend, right? And again, here's one way to think about the sphere, which I had mentioned before. It's like, again, by sphere, I just mean the skin of the orange. I don't mean anything on the inside. So one way to think about the sphere is that you take the northern hemisphere and you take the southern hemisphere, right? And now you're going to glue the hemispheres along the equator. So now glue hemispheres along the equator. Is that making sense? And again, like the sphere itself had no boundary, right? But each equator, right? Each hemisphere has a boundary, which was the circle, right? Here, each piece has a circle boundary. Which goes away after you glue it, right? After gluing. Boom, 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 and then we're finally reaching the point. What is the 3 sphere? Anyone wants to venture? What do you think the equation would be? Anyone sees a pattern here? It was first x squared plus y squared equals 1, then x squared plus y squared plus z squared equals 1. What do you think would follow next? Good. Is that making sense? So that's the 3D sphere. First problem, how do you draw this? I don't know how to draw a fourth axis which is perpendicular to the other three that we already had. So what's the drawing here? I don't know what it is, but I can tell you still that it actually has no boundary. Yeah, like the right. If you fix the value of W, they give you like level spheres. Correct. Good. Yeah. Good. But you see, even if we cannot draw in its full form this new sphere, we can actually still do this picture in terms of the gluing. So here you had two intervals which you glued. Here you had like two half hemispheres that you glue. And what actually ends up happening is that for like, you can think of this 3 sphere as having two balls. So you take two balls, and by balls, I mean that you're actually including the inside. So you actually take like two so now you take two balls, so the interior is included. And the idea is that they, again, if you think about the balls actually have a boundary. The boundary is like the skin of the sphere. So you glue the balls along their sphere boundaries. And so now you are supposed to imagine that you glue the balls along their boundaries. But the point is that this gluing cannot actually be visualized, because you have to take like, imagine taking two origins, and you somehow have to start putting together like the skins of the oranges in such a way that every point on the orange touches another point on the orange. It's not something that you can actually visualize. Like the gluing itself cannot be visualized in 3 dimensions, but that's what's going on. But can't be visualized in 3 dimensions. I actually had two oranges, but I ate them, so I should have been more, have thought more about what I was going to say today. But again, like, buy two oranges, and imagine that both oranges have a north pole, so you have to put the north poles together, right? You have to glue the north poles together, but they also have a south pole, so you have to glue them south pole together at the same time. You have to be doing that for every single point on the surface of the oranges, and that, like, that just something like that cannot be visualized with our minds. But you will get something that's, the thing that you get is actually the 3 dimensional sphere. Oh, beautiful question. Actually, you cannot really tell from just like looking at the equation. Yeah, I don't. I mean, yeah, there's no straightforward way from the equation just to know that um, the manifold is supposed to be simply connected or not. In fact, a bigger issue is that mm, the definition of manifold does not require you to, for it to be given just by a single equation. They're like, the definition is sufficiently abstract or flexible that you don't even need to be able to describe the space by a single equation. So in a way, there can be multiple equations that describe the same, like, different pieces of the universe that are described by an equation. You don't necessarily need like a single equation that describes all the universe simultaneously. So it's a little bit even more tricky than that. It's just that, like, in simple cases, you can actually describe it by one equation, like the case of the sphere. But there are other things that are not just describable by a single equation, but they still can be studied. It's just like a little bit tricky how it's studied. Yeah. Is that making sense? So, actually, the point is that it's like a difficult problem to distinguish, like, to actually tell, like, just from the equation, like, it would be a difficult problem to just like start telling properties about the space. uh well, it's just it's a little bit it's not as straight. I mean, if I give you a single equation, it would not be straightforward to it. Like, let me say it like this: it's not that people made like a catalog of all the possible equations. It's not that there's like a catalog with saying, oh, if this is like the equation, this is how the space looks like. If this is the equation, this is how the space looks like, right? It's not like there's not like a characterization in that form. Uh, the taxonomy is a little bit more tricky. I'll try to explain it later, but it's not that, yeah, you could just go to a list and says that says if the equation looks like this, then the space has to look like this. We don't have such a thing. So, but yet in a way, even if there's not that list, there's a way that at least will tell you that only the sphere uh, is like is the only one with the property of being simply connected. It's a little bit confusing. It's a little bit confusing. It takes some time, but I mean, I think after a few more meetings, this will start sinking in. But it's a bit abstract. Yes, it's uh, it's weird because you're sort of dealing with things that you cannot see, but somehow you can still tell what the properties are supposed to be to a large extent, and you can tell, and you don't really know like what their equations are that describe them, but you sort of still can tell what their behavior is supposed to be. Like it's almost very magical in a way. There's some trickery going on, but I think it probably this is a good place to. The gradients and things like that can be used to some extent, but like you just have to be a little bit more clever. Like in the end, you have to do more clever things to try to understand how the spaces look like. It's not as straightforward. There are like things called like you need more powerful tools, which are called homology and cohomology groups. They're like more like abstract mathematics that you can use. Uh, but it's not yeah, it's like a complicated problem. You like a lot of like actually a lot of mathematics of the previous century was just about this, like how to understand these spaces, like what sort of tools you can use to probe them. So there's a lot of like different things that you can use, but each of them is very tricky to explain individually, let's say. Good. So next time, in fact, what I think we'll do next time is talk a little bit more about 2D universes, just to start getting a feel for one of like some of these tools, what they are supposed to be like, and we'll do a bit of talk about a little bit of the Euler characteristic, which is one of the most powerful ideas in mathematics. And once we talk about the Euler characteristic, I think you will have a better perspective of how you can understand different spaces, and that will help once we well this is like a more philosophical question of what you mean by used for I mean in a mathematical way it is used to distinguish the sphere from other things, right? You could ask whether or not that has any use besides like the intrinsic interest that that could have. Um, Again, this is like similar to the question: is cosmology useful per se, right? Like yes and no, I suppose. So I don't think I cannot bring an application at the top of my head. By application meaning like outside mathematics of the Poincare conjecture. I mean, again, like if you were interested in understanding the shapes of the universe, I suppose to some extent it's useful to know that the Poincare conjecture is true, because people may be interested in knowing what the shape of the universe is. Because, for example, if you had like a way to show that, to prove that your universe is simply connected, not that I'm saying that that's like a super feasible thing, you would know because of the Poincare conjecture that your universe is actually that this sphere. Like, you could still argue whether or not that's a useful thing to know, but that's a little bit more a matter of taste, I suppose. Like, kind of. Well, in a sense, like, the Poincare conjecture, like the proof, or like, let me say it like this way: the proof of the Poincare conjecture uses the fact that you can sort of simplify your spaces in a convenient way, and I'll try to explain that later. So it's not so much like the proof itself requires you to having like understood like how to simplify spaces before that. So the Poincare conjecture per se does not give you the tool for simplifying them, but the proof of the Poincare conjecture requires you to figure out ways to simplify your spaces. Again, like all this sounds very wishy-washy. Is that we just need to maybe talk a bit about other things first, so that you understand what I mean by simplification and other stuff. Yeah. Okay, good. I'll see you next week. We'll go again, discuss a little bit more concrete things for a while, so that you start building up some more intuitions. I think that's useful. Good. I'll see you on Wednesday then. Bye. Bye.
Hey, have a great one.
You too. Bye. Bye.